All right, let's dive in. Today we're going super small, like atom small, to explore the world of solid-state physics. We've got some fascinating research coming out of China, and trust me, this stuff is universally cool. We're talking about the very building blocks of matter, so whether you speak Mandarin or Martian, the concepts here are mind-blowing. Ready to discover how atoms build everything around us from, well, solid things like skyscrapers to the smartphones in our pockets. Let's get this deep dive started.
You know what's really captivating about this field is it takes us to the core of how our world works. I mean, we see and touch solid objects every day, but have you ever stopped to think what's actually happening at the atomic level?
It's true, we kind of take solidity for granted.
Yeah.
So let's break it down, starting with those atoms, those tiny particles that make up, well, everything.
Exactly, but we're going even deeper, zooming into the level of protons, neutrons, and those ever-elusive electrons.
Okay, so it's like taking a normal microscope and giving it like a super zoom function. I'm already hooked. But hold on, I vaguely remember from high school that electrons orbit the nucleus like tiny planets. Is that still how we picture it?
Not quite. That's where the limitations of what we call classical physics become clear. See, electrons aren't those neatly orbiting planets we once imagined. They're more like fuzzy clouds, clouds of probability, each with a specific energy level and a certain likelihood of being found in different regions around the nucleus.
So less about a fixed orbit, more about where we're most likely to find these electron clouds.
Precisely.
Got it. So instead of predictable paths, we're in the realm of probabilities and energy levels. Yeah. Sounds a bit like we're heading into quantum mechanics territory.
Exactly. To really grasp how electrons behave, we need to embrace the strangeness of quantum mechanics, a whole different set of rules governing the microscopic world.
All right, I'm ready to get strange. What are some of those key quantum concepts we need to wrap our heads around to really unlock the secrets of solids?
Well, one of the most mind-bending is wave-particle duality. You see those fuzzy electron clouds we talked about? They actually act like both particles, A and D waves. It's almost like trying to picture light being both a wave and a stream of tiny particles at the same time.
So electrons have a bit of an identity crisis, sometimes a particle, sometimes a wave. What other quantum weirdness should we be prepared for?
Oh, it gets even more interesting. Another head-scratcher is the Heisenberg uncertainty principle. Simply put, it means we can't know both an electron's position and its momentum with perfect accuracy at the same time. The more precisely we nail down one, the fuzzier the other becomes.
Wow, so even at the atomic level, there's a limit to what we can know for sure. That's both fascinating and a bit frustrating for scientists studying these tiny particles.
It definitely keeps things interesting. But let's zoom out a bit now. Let's see how those atoms with their quirky electrons actually assemble to form the solid objects we experience every day. And that's where crystals enter the picture. When atoms bond together to create solids, they often arrange themselves in these incredibly stunning, repeating patterns called crystals. Imagine a perfectly organized 3D grid of atoms, almost like a microscopic Lego masterpiece.
Okay, I'm picturing this perfectly ordered structure, but are all solids crystals?
That's a great question. Not all solids are crystals. Some are what we call amorphous, like glass. In amorphous solids, the atoms are arranged more randomly, but crystals are where we find many of the most intriguing phenomena that drive our technology.
So crystals are the organized, structured members of the solid world, while amorphous solids are more, well, free-spirited. I can see how that organized structure might lead to some interesting properties.
You got it. And to really understand those properties, we need to delve into these repeating units called unit cells. They're the fundamental building blocks of a crystal, and their arrangement dictates everything from a material's strength to its ability to conduct electricity.
So the way those tiny Legos, those unit cells are stacked, determines whether we end up with a diamond or a lump of coal. That's pretty amazing.
Exactly. It's all about structure. The same building blocks can create wildly different materials depending on how they're arranged. That's one of the most powerful concepts in solid-state physics.
So it's not just what you're made of, but how you're put together that matters. And that, I think, is a lesson we can all apply to life in general, right?
Absolutely. And it's this intricate relationship between structure and properties that makes solid-state physics so fascinating and impactful.
Well said. We've covered a lot of ground already, from the quirky world of quantum mechanics to the elegant structure of crystals. But this is just the beginning of our deep dive, folks. We'll be back after a short break to explore the history of this field and uncover how these discoveries have shaped our modern world. Stay tuned.
Welcome back to our deep dive into solid-state physics. It's really remarkable, how we've gone from, centuries of pondering what matter is made of to actually manipulating it at the atomic level. It just shows how even the most abstract scientific ideas can lead to incredible real-world advancements.
Totally. It's like we're standing on the shoulders of all these brilliant minds who came before us. Speaking of those giants, let's rewind the clock a bit. Where did this whole journey into the heart of solids begin?
Well, our story starts, believe it or not, way back in ancient Greece. We're talking philosophers like Democritus and Leucippus. They were already wrestling with the idea that matter was made up of these tiny, indivisible particles. Of course, they didn't have microscopes or particle accelerators back then, so it was all just, thought experiments.
Right, like the original atom smashers, but with ideas instead of, well, actual smashing. Pretty impressive for their time. So what happened next in our solid-state saga?
Things really start to heat up in the 19th century. That's when we see modern chemistry emerging and the atomic theory really taking shape. Scientists like John Dalton, for example, they started to develop a more concrete understanding of atoms and how they combine to make molecules. But it wasn't until later in the century that the focus shifted specifically to solids, and that's where crystals come in.
Oh yeah, we talked about crystals earlier, those stunning repeating patterns of atoms. But how did scientists even know those patterns existed? Atoms are way too small to see with the naked eye, right?
You're right, they are, but scientists started noticing some pretty interesting clues. They observed that a lot of solid substances, they form these geometric shapes in nature, with specific angles and symmetries. Think of things like quartz crystals with their sharp points, or even snowflakes with their six-fold symmetry. Those patterns, they hinted at some kind of underlying order, something going on at the atomic level.
So it was those naturally occurring shapes that gave the first clues, like nature was whispering secrets about the hidden structure of matter.
Exactly. And then boom, in the late 19th century, a breakthrough that completely changed our understanding of solids. X-rays.
X-rays, the ones that let us see through things. How did they help scientists see the structure of crystals?
It all comes down to diffraction. When X-rays pass through a crystal, they interact with the atoms in a very specific way. They scatter off the atoms and create a unique diffraction pattern. Imagine shining a light through a narrow slit. You get a pattern of light and dark bands. It's similar to that.
So it's like the X-rays were casting shadows of the atomic world. I think I'm starting to see the connection here.
And brilliant minds like William Henry Bragg and his son, William Lawrence Bragg, they figured out how to actually interpret those shadows. They developed a technique called X-ray crystallography. And this technique, it allows scientists to analyze those diffraction patterns and determine the arrangement of atoms within a crystal.
That's amazing. So by shining X-rays through crystals and looking at the patterns they made, scientists could actually map out where the atoms were.
Precisely. It was a huge achievement. It confirmed the existence of those perfectly ordered crystal lattices we talked about. And it gave us this incredibly powerful tool to probe the inner world of solids.
Okay, so we're getting a clearer picture of how crystals are structured, but what about the behavior of those tiny particles inside those structures?
Yeah.
How did scientists start to understand what role electrons play in solids?
Well, that's where the quantum revolution comes in, and as you mentioned earlier, it can definitely be a bit mind-bending. See, in the early 20th century, physicists were starting to encounter phenomena that classical physics just couldn't explain. Like, for example, why didn't electrons just spiral into the nucleus? I mean, that's what should happen according to classical electromagnetic theory.
That's a great point. It seems like, well, common sense that those negatively charged electrons would be attracted to the positively charged nucleus and just crash into it. What's going on?
Well, it turns out those tiny electrons weren't behaving like miniature planets after all. They were acting more like waves, spread out in space, each with specific energy levels and a probability of being found in certain locations.
Okay, so back to those fuzzy clouds of probability I see. It sounds like we're entering a realm where our everyday intuitions about how things work, well, they don't quite apply.
Exactly. We're stepping into the world of quantum mechanics, where the rules are, well, different and often counterintuitive. And one of the key figures in this quantum revolution was Niels Bohr. He proposed a model of the atom where electrons could only exist at specific energy levels, kind of like steps on a ladder. They couldn't be in between those levels.
So like electrons playing a cosmic game of hopscotch, jumping between those energy levels.
I like that analogy. And Bohr's model, although it was later refined, was a crucial step in understanding the quantum nature of atoms and how they behave in solids. But it wasn't just about individual atoms. Scientists also needed to figure out how all those atoms interacted with each other within a crystal lattice.
I can imagine those interactions being super complex, especially when you consider all those electrons zipping around with their wave-like behavior and quantum quarks. How did they even begin to make sense of it all?
Well, one of the key players in this puzzle was Linus Pauling, a brilliant scientist who made huge contributions to both chemistry and physics. He really dug into the nature of chemical bonds, the forces that hold atoms together in molecules and crystals. And his work was crucial in bridging that gap between chemistry and solid-state physics.
So Pauling was like the master connector,
Right.
linking the world of molecules to the world of solids. It's fascinating to see how all these different pieces of the puzzle were coming together.
Absolutely. And by combining those insights from quantum mechanics, with the knowledge of chemical bonding and all the structural information from X-ray crystallography, scientists were finally able to start unraveling the mysteries of solid-state physics.
What a journey. We've gone from ancient Greeks pondering tiny particles to actually seeing them arranged in crystals and understanding their, well, rather bizarre quantum behavior. It's like we built this incredible toolkit to explore how matter works at its most fundamental level.
Exactly. And that toolkit has led to some truly remarkable discoveries and innovations, things that have transformed our world in ways we couldn't have imagined.
This is incredible, and I'm sure our listeners are eager to hear about those real-world applications.
Well, get ready, because in our next segment, we'll dive into how those discoveries have shaped our modern lives and explore the exciting possibilities that lie ahead.
Okay, so we've taken this incredible journey through the history of solid-state physics, from those ancient Greek philosophers to the pioneers of quantum mechanics. But now let's bring it all home. How is this mind-boggling science actually impacting our lives today, and what exciting possibilities are on the horizon?
Well, it's easy to forget, but solid-state physics is really the invisible engine driving our modern world. Our computers, smartphones, the internet, all of it relies on our ability to precisely control electrons in materials like silicon. It's where the quantum world really meets everyday reality.
So those tiny transistors we talked about earlier, that's where the magic happens.
Absolutely. Transistors are the workhorses of modern electronics. By manipulating the conductivity of semiconductors, we can create these logic gates and memory circuits that form the foundation of, well, pretty much everything digital. It's amazing to think that by understanding how electrons behave in solids, we can build these incredibly complex and powerful devices.
It's like we've learned to speak the language of electrons, getting them to do what we want. But it's not just about electronics, is it? Solid-state physics is also making a huge impact in areas like energy storage and even medicine.
You're exactly right. One really exciting area is the development of solid-state batteries. Unlike those conventional batteries that use liquid electrolytes, these new batteries use solid materials. And that offers some significant advantages in terms of safety, how much energy they can store, and how long they last.
That sounds promising. What makes them so much safer and more efficient?
Well, for one thing, they get rid of those flammable liquid electrolytes, which is a big safety concern with traditional lithium-ion batteries. And because there's no liquid, there's less risk of fire or explosion. Plus, solid electrolytes could potentially allow us to use materials that store even more energy, so we'd get batteries that pack a bigger punch in the same size package.
So we're talking electric cars that can go further, smartphones that last for days, maybe even grid-scale storage for renewable energy. That's a game changer.
It definitely has the potential to be. There are still some challenges, of course, in terms of manufacturing and cost, but the field is advancing rapidly, and I think we're going to see some really exciting breakthroughs in the next few years.
It's incredible, really. We've gone from manipulating individual atoms to building devices that could completely transform entire industries.
What other areas do you see solid-state physics making a big impact in?
Oh, there are so many. We've touched on medical imaging with MRI machines, but there's a whole world of possibilities beyond that. Solid-state physics is crucial for developing new biosensors, implantable devices, even targeted drug delivery systems. For example, researchers are working on using nanoparticles to deliver medication directly to cancer cells, which could minimize side effects and make treatments much more effective.
Wow, so not just diagnosing and imaging, but actually using solid-state principles to create therapies at the molecular level. It's mind-boggling to think about the potential. But with all this talk about pushing the boundaries of what's possible, are there any potential downsides or ethical considerations we need to be aware of? That's a really important question, and as with any powerful technology, I think we need to proceed carefully and thoughtfully. For instance, the widespread use of nanomaterials raises some concerns about their environmental impact, how they might affect biological systems and ecosystems. We need to make sure we're studying these materials thoroughly and using them responsibly.
It's a good reminder that scientific progress should always be guided by ethical considerations. It's not just about can we do this, but also should we do this and how can we do it in a way that benefits everyone and doesn't harm the planet.
I completely agree. Science and ethics need to go hand in hand.
So we've explored the present, and we've touched on some of the ethical considerations. Now let's have some fun and speculate a bit. What's on your scientific wish list? What breakthrough in solid-state physics would you be most excited to see in the future?
Tough question, but I think at the top of my list would be room temperature superconductivity. Just imagine a world where electricity can flow with absolutely zero resistance, not just at super low temperatures, but at everyday temperatures. It would revolutionize so many things: power transmission, transportation, computing. We could have levitating trains, lossless energy grids, incredibly powerful and efficient electronic devices. The possibilities are endless.
It sounds almost like science fiction. But hey, who knows? Maybe one day it will be our reality.
I hope so.
Any other futuristic possibilities that get you excited?
Another area that's really captivating is quantum computing. We've talked about how quantum mechanics governs the behavior of solids, but what if we could actually harness those quantum phenomena to build entirely new kinds of computers? Quantum computers could solve problems that are just impossible for our current computers, even the most powerful ones. It could lead to breakthroughs in fields like medicine, material science, artificial intelligence, so many areas.
From room temperature superconductors to quantum computers, the future of solid-state physics seems full of mind-blowing possibilities. As we wrap up this deep dive, what's one key takeaway you'd like our listeners to walk away with?
I think the most important thing is to remember that solid-state physics isn't just some abstract scientific field. It's the foundation of our modern world. It's the science behind the devices we use every day, the materials that make up our buildings and infrastructure, the innovations that are driving progress in countless fields.
It's a powerful reminder that even the smallest things, those tiny atoms and electrons, can have a huge impact on our lives. By understanding their intricate dance within solid matter, we're not just unlocking the secrets of the physical world, we're shaping the future of technology and, ultimately, the future of humanity. Thanks for joining us on this incredible journey. Until next time, keep those curiosity circuits firing and never stop exploring the wonders of the world around us.